Okay, welcome. And let me tell you the plan of today. This is the week 9 webinar. We're getting towards the end. This is actually the last Monday evening webinar that we have, because next week is Tuesday because we do every other, but then the following week, I can't do Monday because that's a holiday. So in 2 weeks is a holiday. And so then we'll have a Tuesday also. So the next 2 webinars will be Tuesday and that's it. So I'll let you know the light is at the end of the tunnel in terms of this class. And the plan that I have today, as always, I'll start out with any questions you might have. Always happy to answer questions. Very important. That's a big part of the whole point of doing these live, is so you can answer questions and I can quickly answer whatever you have and then, respond immediately instead of you having to wait a while. Then we're going to do what's called the chi-square distribution. Chi-square distribution is actually really important and used a lot. The math behind it is way too hard for any of you to even have a chance at. So let me just tell you, Kyle, even after calculus is done, you still won't be able to understand how the chi-square distribution works in terms of the mathematics of it. But you get to trust me that I did my calculator right. I'll show you a picture. That's about it. But the math is brutal. So just let you know, we'll see a picture of it. And we've had a lot of distributions in this class. If you remember, we've had the binomial distribution, we've had the uniform distribution, we've had the normal distribution, we've had the student's t distribution. Hopefully you remember all those. And now today we're going to get into the chi-square distribution, which is used in certain instances. If you think about what we've done in this class already, we really have spent all our time, the last few weeks at least, doing confidence intervals and hypothesis testing for either a mean or a proportion. Okay, is everything either a mean or a proportion when it comes to just surveys? What do you think? Is it always a yes or no question or a number answer? Any thoughts? You can pop in the chat. Answers, you say yes, but let me ask you something. What's your favorite color? Put that in the chat box. Okay, now you did not give me a number. You did not give me a yes or no. So no, you have another type of question. Another type of survey question is qualitative, not yes or no. Things like, what's your favorite question? What's your favorite color? Okay, if you're a physicist, you would think of that as a number, but I'm not even going to go there. Another might be, what state were you born in, or what country were you born in if you were born in a different country? And again, that wouldn't be a number. It's not a yes or no. I was born in California. That's not yes. Does that make sense? There are many survey questions where your answers are not yes, no, and they're not numerical. Another typical one would be, what is your ethnicity or race? Okay, and again, that's not a number answer. It's not a yes, no. There are so many different survey questions where you have just words. And that's what we're going to be dealing with today. Okay, we're going to be dealing with how do you handle that? And we're going to have 3 different statistical tests to handle it. One is going to be a chi-squared goodness of fit test. One is going to be a chi-squared test for independence. And the third is a chi-squared test for homogeneity. So those are 3 main tests that are used that can handle these survey questions that aren't yes, no, and they're not number answers. Any questions on that idea first? Again, I don't expect you to understand which is which or what they really mean until a little later. Any questions on that idea? Okay, and I didn't write this as number 6. There's one little thing I want to talk about the project that I didn't get to last time and I want to get to. It's not in the planning of the project, so it was fine. It's in the calculation, and I want to kind of show you what it looks like. So any questions about anything? Again, you can put in the chat box, you can say it, whatever you want. And we are being recorded, so if you say it is public, but that's fine for most people. Any questions about anything? Okay. And by the way, we're moving into chapter 11. That's what this is. And let you know there are only 13 chapters in the book. So we're in 11. We're almost done. Next week, as you might guess, we'll do chapter 12. The week after, we do chapter 13, and that's the end. And then the week after that's just your final. Okay. Which is the same grade as your regular exam, by the way. So just to let you know. Okay. So if there's no questions, I want to talk about the chi-square distribution. I want to do it with it's a distribution that's going to work for this qualitative stuff. And I can't get into the details, at least I can show you a picture. So first thing, there's something called degrees of freedom. If you have more choices for the answer, you have more degrees of freedom, it turns out. So for example, if the survey question is, what season were you born in? How many choices are there for the answer? Hopefully, you know, it's not a strict question or anything. Here's a hint, I was born in the summer. Any thoughts? Yeah, there's 4 seasons. There's 4 seasons in spring, summer, winter, and fall. And it turns out that the degrees of freedom is 1 minus that. So it's going to be 3. And that is a picture of the chi-square distribution when you have a survey question like, you know, what season were you born in? And you can see that first thing is that you'll notice that the x-axis here doesn't have any negative numbers. And the reason it doesn't, I'm not going to get into the details, but it comes from squaring something. When you square something, you don't get a negative number. So there's no 2 tails, there's only 1 tail because there's nothing on the left. Okay, it just stops at 0. Okay, and this is what it looks like. On the other hand, if the survey question might be, instead of that, what month were you born in? Then you would have 11 degrees of freedom. What does it kind of look like now? What's the shape kind of look like? It's not perfect. But what's the shape kind of look like? Yeah, it's a little more normal. If you have a lot of degrees of freedom, and I'll go to the end, then it looks very normal. Okay, it's not perfect, but it looks a lot closer to being normal. But if you only have a few degrees of freedom, here's 1 degree of freedom, it's not even close to being normal, just skyrockets up at 0, actually. Then that's what it looks like. Okay, and that is, again, one of the things to note is that there is no left-hand side. So we're not going to have 2-tailed tests. We're not going to have left-tailed tests. All you have is right-tailed. And so if you do a, you know, some kind of hypothesis test and you look at the value you get, like say it was 8, the p-value will be to the right of 8. It'll be the area to the right of 8, and that's all it is. So you don't have to worry about left tail, right tail, and 2-tail like you do for tests for means or proportions. Any questions on that idea? One more thing is that this right here, this symbol here, it looks like x squared, but that's not x squared. It's kind of a curvy looking x, and that is the capital Greek letter chi, C-H-I. And we read that as chi, and there's a 2 there, so it's chi squared. There's the chi-squared distribution. Okay. You can put it in Canvas, but if you want, you can write CHI if you really want to. Okay. By the way, if you have population mean, I'd rather you write MU than U, because then it's really a mu, not a U. So I noticed that in some of your answers in Canvas or your your exams, you had U. I'd rather see MU. I don't think I took out points, but for now on, use MU if it's mu. Okay, and for chi, use CHI. Okay, any questions on that? Okay, so that is the distribution. What we're now going to do is we're going to do some examples. We're going to do some examples. We're going to need to use this distribution for a hypothesis test. And again, feel free to ask any questions you have throughout, because that's what this is all about, was to make sure that you have time. Okay, so here's an example. Okay, and I got this online. In California, 39% of residents are Latino. 35% are white. Okay, so whites aren't even, the majority or not even the number one race in California. Okay, Latino are. 16% are Asian and Pacific Islander, and 10% are other races. Okay, and that could be Native American, it could be Black. Those are the main other races. Okay, is the distribution of races different in California community college students? Because what we would like, let's say you're the chancellor on the board of the California community college system. You want to be representative of the state, right? So we hope that, in the California community college, it would be nice if we had 39% Latinos, 35% white, 16% Asian Pacific Islanders, and 10% from other races. Wouldn't that be a good thing? Then we know that, there's no discrimination. We're just right on track. So that's what we hope for. Okay, but if it isn't, then you got to say, well, now we got to deal with it. Because that means maybe, who knows, maybe there's discrimination, maybe it's hard for a certain race to get in or whatever. Any questions on that? Okay, so now a survey was done. And by the way, when I say a survey was done, I'm just making this up. We can pretend a survey was done. Of 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. So notice a survey question here is, what is your race? And whatever you say, you put it in one of these categories, right? There's not a number answer. It's not yes, no. It's what is your race? And what can be concluded at the 5% level of significance. By the way, you would probably use 5% level for this. This is very, like sociology kind of thing. And whenever you're doing sociology, use 5%. It's standard for most things, and definitely chi-squared. Okay. Any questions on the question? Any questions on the question? Okay, one thing to note is that this, if we try to use anything that we've already done in class, this won't work, because this is not a difference between two means or a single mean, because this isn't quantitative. It's not a difference between two proportions or a single proportion, because this is not a yes/no question. So we have not encountered anything like this before. Any questions on that idea first? Okay, the question is, what is your race? It is a qualitative answer. And when you have that for this class, we're going to be using chi-square distribution. Okay, in particular for this one, we want to write down, you're still going to have an H0 and H1, and I want to give you a little warning. And that is, in this chapter, our H0 and H1 will be written in words. But in all the prior chapters, when you're talking about a hypothesis test, so in chapters 9 and 10, symbols were what you had to use, like mu1 equals mu2, or p is less than 0.75 or something like that. But with this chapter, we're using words. Next chapter, we're going back to symbols again, by the way, just let you know that. But ready for words here. Okay, so here's the words we use. So first thing, H0, you're used to that. That's just the null hypothesis. And it says the distribution of races at California community colleges is the same as the distribution of races in California. Okay, so notice I highlighted the word distribution. Okay, with this kind of test, if you don't put the word distribution in, I will take off points. Got it? Okay, and by the way, we got 3 different tests. So this one is going to have distribution because we want to see if the distribution of this unknown, which is a California community college, is the same as the distribution of the known, which is California. Any questions on that? Okay, the good news is H1, the alternative hypothesis, is exactly the same with one extra word, not. So the distribution of races at California Community College is not the same as the distribution of races in California. Any questions on that? Okay, and again, you have to have that word distribution. Okay, that's really important. All right, the test we're going to be using for this is called a goodness of fit test. Because what we're looking at is, if we look at the distribution of races of the survey that we did of California Community College System, we want to say, is that a good fit? Okay, or is the races of all California a good fit for what we got? Or is it just really different? Any questions on that? Any questions? So that's why we call it a goodness of fit test. And that is when you have a known distribution and an unknown distribution, and we want to say, is a known distribution the same as the unknown distribution? Any questions on that? Okay, so this step-by-step process. The first step, and we've seen this before, is to decide what is your H0 and H1. And that's what I just talked about. The second step is to write down a table. And we often call this the observed and expected table. So I'm going to use O for observed and E for expected. Then for the column headers, we're going to have Latino, we're going to have white, we're going to have Asian Pacific Islanders, and I'm going to have other, because those are the 4 races that are the possibilities for this survey question. Any questions on this idea so far? Okay, now I need to put my numbers in. And the observed are actually really easy because we just look to see what we observed. How many Latinos were observed? Put in the chat box, how many? Or say it. Yeah, 125. Because it said, for the study, for the survey, 125 were Latino. So I just put 125. How many whites were observed? Very easy. Yeah, 92. So hopefully you see how easy this is. How many Asian Pacific Islanders were there observed? 33. And then how many others? 50. Any questions on that? So the observed's easy. Just put in what they told you. The expected, we have a little bit of work to do. So for the expected, what we have to do is we have to say, well, we surveyed 300 California community college system. Okay. The expected means that if H0 is true, how many Latinos would we expect to get from our survey? Well, there are 39% should be Latino. Okay. But we surveyed 300 California community college students. So what we're going to do is we're going to take 0.39 times 300. And that's how many Latinos we would expect to get if we really got what this percent, the 39%. And then 0.39 times 300 is 117, right? Yeah, and you can pop that in your calculator if you want. Any questions on that? So we're going to have 117 for our observed Latinos. Okay. 35% are supposed to be white. Well, we do the same idea. 0.35 times 300. And that's 105. And that would be our expected number of whites. Any questions? Okay. Then for the Asian Pacific Islanders, 16% are Asian Pacific Islanders. That's 0.16 times 300. And that's 48. Again, you're always welcome to put it in a calculator. You don't have to do what I do, which is do it in my head. Just stick in a calculator. Okay. And you get 48. So 48 for the Asian Pacific Islanders. And then we have our others. Well, 10% are other races. So that's 0.10, 10% times 300, and that's 30. That one you might be able to do in your head. 10% is easy. Just drop the 0. Okay, and then we get 30. Any questions at all on creating the observed and expected table? Any questions? All right, so the next step is what you're used to. What do you usually do after you get all the numbers? For a hypothesis test? Yeah, we use your calculator to find the p-value. Okay, not going to add them, we're just going to use the calculator. So let's go to the calculator. And I think I lost already, so I'll go up here. Uh, 46, there we go. We're almost at the end of the course. What calculator number do you think we're going to use? I tried to make it obvious. Yeah, because we said this was a goodness of fit test. So we're going to use calculator number 21. And I click on it. Okay, and what it says is type in the values from the observed and expected sets separated by commas. Okay, then calculate, then hit calculate. And it'll just do it for us. So let's go back. And my observed are these guys. I can copy and paste, and I got to put commas in. So 125, comma 92, comma 33, comma 50. And my expecteds. Copy and paste. And I got to put commas in. Okay. And by the way, if you ever have a number like 100,000, don't write 100 with a comma and 000. Don't put a comma in your number, because then the computer gets confused about your commas. Okay. Any questions on putting in the observed and expected values? Okay. Next step, hit calculate. Okay. And Our test statistic is chi-squared. And this number about 20.2 or so. Our p-value is right here, 0.00016 or so. So let's write that down, 20.177. For our chi-squared. And our p-value is 0.3016. Any questions? Any questions on finding the test statistic and the p-value? Any questions? All right, so the next step is to write our conclusion. Okay, well, look at our p-value. What's the first few words of the conclusion? Okay, reject the null hypothesis is definitely what we're going to do. And then what's the first few words of the sentence that we put in? It's the same as what we've done the last few weeks. No. All right, maybe I'll write it out. There is, do you remember that? That might help. One of the next couple words. Same as last week and the week before. Yeah, statistically significant evidence to support the claim. That. And the nice thing about having it in words is I can copy and paste. Just change the grammar a little bit. Maybe change the color too. Okay. And lowercase t, the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions at all on this conclusion? Any questions? Okay. Just a note, something that we're not going to be able to do in this class is we're not going to say why is it that they're different, like which is the one that's different. Is it the there's more Latinos, there's fewer Latinos, more whites, fewer whites, you know, which race is the one that's different than it should be? Does that make sense? Okay, it doesn't mean that can't be done, but if you want to learn how to do it, I'll let you know you need to take an upper division statistics class. So this is elementary statistics, so we can't get that to the next step. But there is a next step, and we can only do so much in our class. I rarely have anyone complain that we don't do enough stuff in our class. Everyone's like that, they're exhausted by the end. But let you know that there are statistical tests to go further, but we're not doing them in this class. Any questions on this idea? Okay. By the way, what would change? Let's say, you know, numbers were different and we got a p-value instead of this 0.00016. Let's say p-value is 0.73. What would change? Not much. What would change? Yeah, I mean, the idea changes a lot, but the wording doesn't change much. And again, this isn't new, this is old stuff. Yeah, you take this word significant and you write insignificant instead. So if you get a large p-value, there would be a statistically insignificant evidence to support the claim that the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions on that idea? Any questions? Okay, so that's good as a fit. We'll do another example good as a fit too for a different way of looking at it. But for now, we've got some. Good as a fit, you're often going to be looking to see if the distribution fits a distribution that you know about that comes from data or some website. Sometimes you'll look to see if the distribution is uniform. So you might say, I don't know, is all 4 seasons is the distribution of seasons for birthday, is that uniform? Do you think it is? In America, maybe. Okay, you think not, right? My guess is you don't know for sure. You'll never know for sure, but what you could do is you can do a survey. You ask people what season were you born in? Spring, summer, winter, or fall? You ask, maybe 500 people that. And then you do the chi-square test. And if it's uniform, if you asked, let's say you asked 800 people, then your expected values would be, for each of them would be 800 divided by 4, because it's 4 seasons. And if they're this uniform, that means they're the same. So that means you just divide by how many there are. Any questions on that idea? Okay, so that's how you can handle testing to see if you have a uniform distribution or not using a hypothesis test. And we want to be able to do hypothesis tests. So far, so good? Okay, so let me do a next example. Okay, so now this one's a little different, but I kind of hinted by going into the seasons, but actually it's going to be very different. Okay, does it matter what season a person was born in when it comes to the type of car they drive? Okay, maybe everyone who was born in the summer tends to drive an SUV. I don't know. So what you could do is you can conduct a survey. In this case, you would ask 2 survey questions. The first survey question would be, what season were you born in? And the second survey question would be, what kind of car do you drive? Sedan, SUV, or other? Any questions on that idea? And we have a table. And you often call this a contingency table. What we can say, for example, this number 62, that means of the people who were surveyed, 62 of them were born in the winter and drive an SUV. That's how you read this table. Any questions so far? Okay, so now we've got to say, can we use goodness of fit test for this? What do you think? We use goodness of fit? Not sure? Okay, the answer is no. You cannot use goodness of fit because we're not seeing if the distribution of something is the same as the distribution of something else. Okay, this is not an observed and expected type of thing. Okay, there's no observed and expected. All we have is 2 survey questions. Okay, and what we want to do is we want to say, if you're given information about their birth season, will that help you or provide information about what kind of car they drive? It's very different than asking if the distribution of 2 things is the same. Okay, but we have done something similar to this, but you may not like it when I say this. We did it in chapter 3, like a long time ago. Okay, and we wanted to say, knowledge of one, does that help you with the knowledge of the other? We checked to see if things were independent or dependent. But now what we're going to do is we're going to look at, in general, season born versus car type. Are they independent or dependent? We're not going to look at a specific item. Okay, in chapter 3, we looked at specific items and we could test it. But now we're going to be looking at, just in general, season born and car type. So the test we're going to use is called the chi-squared test for independence. Still a chi-squared test, but now it's for independence. Okay, it's when we have 2 survey questions. They're both qualitative questions, and we want to see if they're independent or dependent. Any questions on this idea? Okay, so here's H naught and here's H1. H naught is season a person was born in and car type are independent. Notice that word independent. If I highlight it in red, what's going to happen if you do not put the word independent? If you're doing a test for independence, let's say on the exam. Yeah, point deduction. So you don't want deducted points. So make sure that you get the right wording in. That's required. Okay. And just know, I just graded your exams and I graded your discussion posts. I woke up early in the morning, was able to get it done, a lot of hours in the morning. And I did notice that some of you did not put in, and when I say some of you, I mean of the whole class, did not put in some of the keywords I told you had to put in for chapters 9 and 10. Population mean and population proportion. You have to specifically talk about the population. Here, if we're doing a test for independence, you got to specifically talk about independent for H naught and dependent for H1. So H1, it's very similar. Season a person was born in and car type are dependent. Any questions on that? Okay, and I do take out points if you don't have the wording right. All right, here we already have our full table. There's not observed and expected. It turns out there is something called an expected table, but I'm not going to get into that. You don't really need to for this class, but there is something like that. We don't worry about it. We don't need it for what we're going to do. And that is because, any guess on what the next step is going to be? After you've written H naught and H1, we have all our numbers. Yeah, we're going to use a calculator. So let's do that. What calculator we're going to use? Yep, 22, test for independence. I tried to make it obvious. Okay, so I click test for independence. And here, it gives you a big table. And by the way, if it's a bigger table than you need, just leave the other stuff blank. I do want to also let you know that it turns out that if you switch rows and columns, that doesn't change anything. So you can do that. It's not a problem with this example, but let's say you had, instead of 4 columns and 3 rows, let's say you had 8 columns and 3 rows. The problem is there's only 5 columns here, but you can kind of switch it and you can do 8 rows and 3 columns instead. So you can just kind of put it on its side. And the calculator works and it's fine to do that. Okay, so, and that usually works. And by the way, anything more than 5 by 5, that'd be too much typing. I'm not going to have you do that. In the real world, it can happen. And if you have to do that, then you use a spreadsheet like the one I created, which I'll show you a little later, by the way. I won't show you the chi-square, but we'll open up the spreadsheet. But in our class, we're not going to have anything bigger than that. Okay, but what we do have to do, we have to read the numbers out. 73, 81, 76, 78. So 73, 81, 76, I think 78, 73, 81, 76, 88, 78. The next is 65, 68, 62, 64. So 65, 68, 62, and 64. And then the next row, 43, 51. And then 48, 50. Any questions at all on entering the data? Okay, then you scroll down and you hit calculate. Okay, try to make it pretty easy to use a calculator. But you still got to type numbers in that you can't get around. What do you notice about chi-squared and p? Chi-squared, that's our test statistic, about 0.48. And the p-value, 0.998. What do you think we say? How does it start? Our conclusion. What are the first few words? Yeah, statistically insignificant. This p-value, this is bigger than any level of significance you can even imagine using. Okay. And by the way, if you're not given the level of significance, then you use the kind of vocabulary with strong evidence versus weak evidence versus just insignificant. This is truly insignificant. So there is statistically insignificant evidence. To conclude that, and then I just copy and paste H1. Maybe make the season lowercase. The season a person was born in and car type are dependent. Any questions on that? Any questions? Okay, test for independence is really important. Okay, it really is important. Any questions at all on this test for independence? Okay, you often use it, for example, in business. You want to find out if two things are independent, and if they're dependent, then you're going to have different advertising strategies, right? Because then you're going to advertise to a certain group to do a certain thing, because that means you're going to be able to get information. If they're independent, then you just do a general advertisement. Any questions on that? Okay, so for example, and you might have noticed this happens a lot on the internet. When you go on the internet, it's going to send advertisements in your face, and it tries to advertise things that are for you. And it's decided what's independent and what's dependent when it comes to people buying stuff. And if it finds out that it's dependent and you're on that side, then it'll advertise to that side. If it's independent, then it's meaningless to use that for advertisement ideas. So that's one example. And that's how it's used. And it's usually used with AI on that one. Okay, but someone had to program that in, and they're testing for independence and dependence. And then if it's dependent, then you go further. And we don't go further in this class because it's elementary stats. So any questions at all on the chi-squared test for independence example? Okay. All right, if there's no questions, then what I'll do is go to the next example. Okay, so here I have another example. And what it says is, do single men and women take the same type of vacation? Okay, the table below shows the results of a study. Notice we have male and female. Okay. Okay, and the types we're looking at are international travel, out of state, and kind of more local. And here we have, and by the way, I made up these numbers, but you can imagine a study being done. It's just 2 survey questions. One is what, is your gender. And we're just looking at men and women. You could do a third, but then it would be test for independence instead. You couldn't do it this way because you can't compare 3 things. Okay, so then we're going to have international, out of state, and more local. So the second survey question would be, what type of vacation maybe did you take last time? International, out of state, or more local? And then the person answers. Any questions on that idea? And then you can see that, for example, 33 men went more local last time they traveled. Any questions at all on kind of reading this? Okay, this is different than saying, are they independent or dependent? We're looking at 2 groups, and we're saying, are they the same in terms of the answers to this survey question? Okay. So we're not going to use test for independence. Can we use chi-squared good as a fit? What do you think? Yeah, no, you can't, because chi-squared good as a fit is where you know one population and you don't know the other. Here, we have 2 populations, the male and the female. And we don't know either population data. We only have samples for each. Do you see that? So you can't use good as a fit. You can't use independence. We're going to have a new test. And the test is chi-squared test for homogeneity. Okay, so that's the words you use for this. It's called the chi-squared test for homogeneity. And we use that again is when we're looking at 2 different groups or 2 different things and deciding whether they have the same distribution. So why can't use it for independence? So we're not saying, are they independent of each other? We're saying, is the distribution of traveling the same for men as it is for women? The reason on this that you can't use test for independence is what we're looking for is not about them being independent or dependent. We're looking to see if the distributions is the same. And it's of 2 distributions that we don't know either of them. Does that make some sense? Yeah, so it's different than independence. Independence is when you find out 2 survey questions, are they independent of each other? Here it's, are the distributions of one group the same as the distribution of another group? All right, so here's the H naught and H1. H naught is the distributions of vacation type are the same for men and women. Notice here, unlike chi-squared for good as a fit, where it had distribution, this one has distributions. because we have two different distributions. We don't know either of them, and we want to find out, are they the same as each other? H1 is the distributions of vacation type are not the same for men and women. Any questions on H0 and H1? And again, you need to refer to that distributions for H0 and H1. All right, what do you think the next step is? Yeah, we go to our calculator. What calculator number do you think we're going to go to? Yeah, 23. And you should get a little excited, by the way. How many calculators are there? Yeah, there's only two more. And remember, that's what this class is all about. We have very little left in this class. We're almost done. Okay. All we have left, as you guess, next week will be regression analysis. The week after will be ANOVA. And that's all we've got left in this whole class is regression analysis and ANOVA. And then we're finished with this whole class. Okay. But we got to finish homogeneity, of course, because we haven't finished the example. But I can click test for homogeneity. And here, enter the observed values for each of the two samples A and B, hit calculate, and the chi-square test statistic and p-value be calculated for you. Leave blank the last rows that do not have data values. So what I'm going to do is I'm going to put them in. So we have 29, 47, 33. So 29, 47, 33. And then we had 38, 42, 36. Any questions on entering the data in? Okay, then you just scroll, hit calculate. And there we go. And we have our chi-squared. And as I mentioned today, this chapter, everything is chi-squared. Okay, they're different tests, but it's the same test statistic. It's chi-squared, or at least the same name of. So 1.40 maybe. And the p-value was 0.496. By the way, I want to mention, because some of you, you as in the class, didn't pay attention. I do take out points. You got to use the rules of rounding. Do not write 0.495 because the rules of rounding said the 6 makes the 5, add 1 to the 5. Okay, so make sure you pay attention to rounding. And then we write our conclusion. What are the first few words? Again, hopefully you're used to this now. Yeah, there's statistically insignificant evidence because 0.496 is bigger than any level of significance you'd use. There is statistically insignificant evidence to conclude that, and then I copy and paste H1, which is what I always do. And take that T and make it lowercase. That the distributions of vacation type are not the same for men and women. Maybe I should make them the same. Ooh. Let's do this again. That's better. Any questions? Okay, the chi-squared. So let's look at this. Chi-squared is 1.4. And by the way, this is a 2 degrees of freedom. So if we go back here, it's going to take a minute to get there. Show you what's happening. So we had 2 degrees of freedom. We'll see that our chi-squared value was, where was it? There, was 1.4. So 1.4 is around there. It's like close to 2, close to 2. And if you look at the area to the left of that value there, that area is 0.496 or so. So that's what the chi-squared value does, is it puts it up on this graph, and then the p-value is the area to the right of that p-value. So the area to the right, of that chi-squared. The area to the right of the chi-squared is the p-value. That's how all this stuff is right, or sometimes left if you're doing a left-tailed test, but with chi-squared it's always right-tailed. So that's where that's coming from. And you can see the picture, and clearly the p-value is not small with 1.4 for the chi-squared. So that just from there, you can look at it and see that you fail reject. Okay, so now that we have that, let's do one more example. Oops, I made a mistake. Okay, so one more example. So a study was done asking people how far they traveled for Memorial Day weekend. Okay, I don't know how far you all traveled, but I traveled about, probably from my house, maybe 5 miles by foot. I do a lot of hiking, but that's about it. Maybe 8 miles. I didn't travel a whole lot, but some people do travel. The mean was found to be 120 miles, and the standard deviation was 40 miles. The table shows the results. Is the distribution normal? Okay. So let's take a look at this. First thing is less than 80. There are 56 people who said they traveled less than 80 miles. Okay. There were 61 who traveled between 80 and 160 miles. And there were 12 who traveled greater than 160. Any questions on just looking at that data? Okay. There's a reason why I'm choosing this 80 and 160. Do you see why? You see why I'm choosing 80 and 160 as important numbers? Here's a hint. We want to see if the distribution is normal. Don't see you jumping in. Greater than 30, not about 30. No, it has to do with the 120 and the 40. If I go one standard deviation to the left, then it's 120 minus 40, that's 80. If I go one standard deviation to the right, it's 120 plus 40, and that is 160. Any questions on that? Okay, so let's drop that for now. So first thing, the sample size was 56 plus 61 plus 12, which is 129. Let's make that a little bigger so you can see it. How many would you, if it's a normal distribution, what percent would you expect to be within one standard deviation of the mean? Do you remember that? That was a long time ago, chapter 6. Do you remember what percent you would expect to be within one standard deviation of the mean? No, that's two standard deviations, 95%. Yeah, one standard deviation was 68%. I don't know if you remember that number, but that happened in, again, in the normal distribution chapter. So I'm going to go 0.68 times 129. Any questions on how I got that? Okay, then, by the way, I can go in, there's a scientific calculator, I can pop that in, and 87.72, I'm going to round to the nearest whole number, so 88. Any questions on that? Okay, now the normal distribution is symmetric. So if there's 88 inside, maybe I'll use a decimal place just for fun. 88.72. Then we could say either 88.72, or you could just say if 68% is inside, then 1 minus 68% is outside. Any questions on that? And then half of that will be to the left. So what we're going to do is we're going to take 1/2 times 1 minus 0.68. So a half of the outside will be the left. And then times 129. And we can pop that in, see if it'll allow it. Did some weird formatting. Yep, that's 20.64. So the left will be 20.64. The center will be 88.72. Any questions on that? And the right, well, the left and the right should be the same because the normal distribution is symmetric. So it's 20.64. Anybody lost? That's, for a lot of people, that's the hardest part, coming up with these expecteds. Okay, what kind of test do I want on this one? What test? Yeah, this is a goodness fit test because we want to see if an unknown distribution, right? Distribution of how far people travel on Memorial Day weekend fits a known distribution. The normal distribution is very known. So this is good as a fit. Any questions on that? Okay, if it's good as a fit, then our H naught is the distribution. That word has to be there. Of Memorial Day weekend travel is normal. And H1 is the distribution of Memorial Day weekend travel distances is not normal. Any questions on that? We've seen this a lot, or we've talked about this a lot, where we said, well, our sample size is too small, so we have to assume a normal distribution. Well, that assumption is like scary if you have no clue. But if you can do a chi-squared test for normality, you can see, hey, maybe maybe you're not as worried that it's not being normal. Any questions on that? Turns out there's more sophisticated tests for normality, but I can't get into those. That is, again, more of an upper division stats class called a Kolmogorov test for normality, which we're not going to do. But it basically kind of integrates the chi-squared more densely. So what's the next thing we do? Yeah, we use a calculator. What calculator should I use? What number? Yep, 21. We're doing a good as fit test. We need to write the observed separated by commas. So 56, 61, 12. And 20.64, 88.72. And 20.64. Any questions on that? You calculate. All right. The chi-squared is 72.9 about. What's the p-value? Okay, this is a big warning. Okay, it's not 1.11 or 102 or even 110, 1102. The p-value can never be bigger than 1. It's p-value is a probability. You can't have 111% chance of something happening. What are you missing? You just got to move your eyes to the right spot. Can you see? Yeah, this E negative 16. That means we need to move the decimal 16 places to the left. And then you have the 111. So P is actually basically, it's as close to 0 as you can imagine. 0.000, a whole bunch of zeros before you get to 111. Do not write ever a p-value bigger than 1. That means you are not reading it. Any questions on that? Very common error. All right. So if we have a p-value that's small, what does that tell you? Yeah, statistically significant. And you could even really highly, or there is extremely strong statistically significant evidence to conclude that, and then we can just copy paste. The distribution of Memorial Day weekend travel distances is not normal. Okay, this is one of those where the p-value is so small, you would like just put your life on it. You know, this is one of those you gamble anything on this one because it's not going to happen. Any questions on this conclusion? Okay, what do you think the hardest part is going to be in this chapter? What's the most challenging? And I know this because I've been teaching a long time. Yeah, good. Finding the right test, deciding what kind of statistical test is it? So the first thing you do is you say, what's the answer to the survey question or questions? If the answer or answers are not yes, no, and not a quantitative numbers, then this is chi-squared. Okay, then you say, is there a known distribution and an unknown distribution in which you're comparing the unknown to the known? Then it's goodness of fit. Or maybe, is it two survey questions at which both are just qualitative, not yes, no, and you want to say, is a relationship between the two? That's test for independence. Or maybe there's two survey questions. One is basically you're looking at one, which gives you which of the two groups someone's in. And the other is some other qualitative, not yes, no, not number survey question. And you want to find out, do the groups have different distributions? Then it's homogeneity. Okay, so those are the three kinds of tests. It's very important to get those down. All right, what I want to give you, we're not done yet, but I want to give this to you because it's about time, is the secret word. The secret word for this week is distribution. Because in good as a fit, if you don't know that word distribution, you lose points. So that's the secret word for this webinar. Any questions on the secret word before I move on? Hopefully both of you are watching. Okay, what I want to talk about now is a little bit about the project. And I want to remind you, this is not project 1. This is project 2. Any guess what I'm going to have to do when I'm on the spreadsheet, which you have to use spreadsheet, by the way. Any guess on what you're going to have to do with the spreadsheet for project 2? What's your thoughts? The hint is what we're looking at now is not what you're going to use. I don't see you jumping in. We're going to use this two-var stats tab. Okay. By the way, we're not doing chi-squared. Do not do chi-squared on your project. Okay, you will not get very many points if you do chi-squared. This is a two-variable stats tab. So you click on that and you'll notice there's A and B. There's a first and a second. First thing you're going to want to do is you're going to want to highlight the numbers with first and second and hit the backspace, and that sends them blank. Okay. And by the way, you'll notice everything becomes nada and whatever because there's no numbers in yet. Then we're going to put your data in. You have your data from the first. I'm just going to make up some numbers. So 4, 5, 2, 7, 9, 8. Okay. You're going to have a data. And by the way, you have to have at least 31 for the first data set. And for the second, you also have at least 31. That might be 6, 7, 1, 9, 2, I don't know, 7 again. Okay, now you can have a lot more data values, but I don't want to waste your time. Any questions on getting these data values in? Okay, now the next step is moving your eyeballs. And you have to, based on your study, you have to know we're using independent or we're using dependent data. Okay, and it really depends. Okay, it really depends. So it depends on your particular project. If you're using independent data, then the J and K, those are going to be the important things. And you'll notice that there's confidence, there's a hypothesis testing and confidence interval. And here you have to know, are you using a two-tailed, right tail, or left tail? And you read the p-value that corresponds to what you're doing in your project. Everyone's project will be different. Okay. You choose your level of confidence. So notice we have a confidence, a lower level, a lower and an upper bound for the confidence interval. And that's for 90. If we want it 95, you go 95 and you type those in and you hit enter, and that will change it. You can go and you can look very easily at the different confidence levels. By looking at those, you can see which the client will be happiest for. Remember that if you have like 99%, that means you're happier in that you have a much smaller chance of being wrong. The problem is the margin of error gets bigger. So it's a give and take, and you have to, in your project, you have to talk about which is the best to use based on, and again, you should look at 90, 95, and 99. And then based on the give and takes, then you make the decision which is best for your client and why. And you should explain that in like a paragraph. And then you go over your confidence interval. And don't just do the template, write a whole paragraph about it. You should be interpreting and talking about what decisions the client will make based on the lower bound, what the decisions the client will make based on the upper bound. Okay. And by the way, I'm looking at independent. I'll show you dependent. It's not that much different. You should also look at the standard error, what the decisions and issues the client will have based on the standard error. And really talk about the standard error like a lot. Any questions on that? Okay. And you should also look at the p-value, whichever one is relevant. And that's what you have. And here's your test statistic, by the way. If you're using dependent data, that's going to be, instead of J and K, it'll be N and O. It'll be these guys. And again, you have your p-value, you have a confidence level, same idea though. So that's really important for the project. The project is all about understanding and interpreting and talking about the decision the client is going to make from each of the numbers that we're looking at over here. Any questions on that? Okay. And then in your project, let's say you have dependent, you're going to copy and paste N and O into your paper and put that on a page. Okay. Whereas if you have independent, you'll copy and paste J and K into your paper. Okay. And get the right one down. And again, we're here to help. Tutors are here, and I'm here also. So, don't get it wrong. So I figured I should mention that because it's very, very important. Any questions at all about the project? Any questions? Okay, if there's not questions about that, as I think I mentioned that today's a little bit shorter, there's a little less to do today. We had a little bit about the project. Kind of gets easier at the end of this class. That's what I do, is I lighten up a bit towards the end. A little less work in the last few weeks. Okay, but you do have your project and you should be thinking about it. Again, the project is chapter 10. Don't even think about chapter 11 or 12 or 13 for your project. It's all about chapter 10, and it can't be proportions. It has to be means. So it's this, what we're looking at now, either independent or dependent. Okay, so if there aren't, then what I'm going to do is I'm going to stop the recording.